Good morning, everyone. We are from Wong Secondary School and with team number 51093. Our research topic is constructions of tangent to circle in Poincaré model. Our presentation will be divided into 3 parts. First, I will give the introduction to the Poincaré model, and I will introduce elementary constructions, and finally, we will give the solution for our 3 problems. First, let me introduce the Poincaré model. It is describing the hyperbolic geometry. It consists of a unit circle in a complex plane. We denote D as any spaces inside the unit states, and U as its circumference. And then what is a straight line in this model? It is called D line, and is defined as part of a generalized circle which meets U at right angle and lie inside the Poincaré disk. And then we define the distance between 2 points in the model by these formulas. And there are 2 notes we should aware when we see the definitions. First, for an equal hyperbolic distance, the farther away from the center of the disk, the shorter the apparent distance. And secondly, if one of the points is on the center of the disk, the formula can be simplified by this. And in our research, we often rely on this formula to calculate the distance. And then what is the circle in this model? It is called hyperbolic circle. Actually, it has the same definition with Euclidean circle, but the center is shifted outward owing to its hyperbolic radius. And then what is the angle between 2 D lines? It is just a Euclidean angle between their tangents. And then what is a tangent to a circle? It is a D line touching the circle at one point. And then how can we define inverse point? We can look at the figures for the illustrations. We can see that B is the inverse point of A with respect to the circle if and only if OA times OB equal to R squares. And the inversions has an important property in the model. When we reflect a point in the D line, the point and its image are the inverse of each other with respect to the D line. And under the reflections and translations, angles and lengths are preserved in this model. Now, in order to move one step toward as a research result, I would like to introduce what construction tools we have used in the research. In our research, we can construct the following things with Euclidean complex and straight edge. It includes the inverse points, D lines, hyperbolic circles, and perpendicular bisector. Besides the above tools, we also need a very important theorem, which is divided by us to help us to solve our problems. And what is this about? It is in a situation when given a circle C, and given a Euclidean with radius R, and given a circle C with the center at the origin, and with the radius of R, we can construct a circle which is orthogonal to C and touching C at one point. But how can we find out the radius of these circles? That's easy. We just use a simple geometry theorem called Pythagoras theorem. By looking at the right angle triangle, we can obtain the relationship. We can obtain these equations. And by simplifying these equations, we can obtain the relationship between the capital R and the small r. This comes to a very important conclusion that when given a Euclidean length R, we can construct a line segment of length with capital R using complex and straight edge. Thus, this helps us to solve our problems. And then, what are the 3 problems we are going to solve? Now I will show to all of you. The first problem is construct the tangent at a point, tangent from an external point, and then common tangent to 2 circles. And for the first questions, when given a circle C1, and then we can draw a tangent to C1 at A. First, we try to draw a perpendicular bisector between O and B, and then find an inverse point of A with respect to this perpendicular bisector called A dash, and then construct a circle C1 dash with respect to this, with center O and passing through A dash. We call it C1 dash. And let the radius of this circle be R. The purpose of doing this is to move the circle to the center of the disk. And then, by using our theorem, we can construct a circle which is orthogonal to U and touching C1 dash and with the Euclidean radius of capital R. That's this. But how can we locate the centers of this circle? First, we draw a circle with center at O and then with the radius of capital R plus small r. And then draw a Euclidean straight line passing through O and A dash. And obviously, the intersection points of the circle and the straight line will give the center of our required circles. Now we try to draw the circle. The circular arc inside U will give us the tangent to C1 dash at A dash. That's this. And now we are going to the last step. Now we are trying to find the inverse of this tangent with respect to this perpendicular bisector. But how can we do this? First, just randomly assign a point on this tangent, and then find the inverse point of this point with respect to this perpendicular bisector. And finally, construct a D line between these 2 points. And so we finish drawing a tangent to C1 at A. So our first problem is solved. And for the second problem, when given a circle C1, we can construct a tangent from A to C1. Actually, for this problem, we can use the same technique from problem 1. First, we try to find the inverse of point A and move the circle C1 to the center of the disk by using the perpendicular bisector between O and B. Again, by using our theorem and the same approach from problem 1, we can construct two circles which is orthogonal to U and touching C1 dash and passing through A dash. Now we are going to the last step. Try to find the inverse of these two tangents. And so our second problem is also solved. And for the final problems, since we try to draw the common tangent to two circles, since the same techniques can be applied to this problem, I'm not going to show the step in details, but we'll just pay the steps to all of you with some explanations. First, we try to move one of the circle to the center of the disk and also move another circle accordingly with respect to the perpendicular bisector between O and A. And then, again, by using our theorem, we can construct one of the common tangent to C1 and C2. And then by doing the inversions of this tangent, we can construct one of the common tangent to C1 and C2. And for the other three common tangents, we can use the same technique to draw it one by one. So our first problem is also solved. After the submission of our report, we have done further works. We have investigated circle packings and tessellation in Poincaré model. And we see that in the figures, all circles are congruent, and each circle touches n circles, that's denoted by n, and each hole is surrounded by k circle. So in this figure, the case is, we denote it as 6,4 case, and then the Euclidean radius of the central circle is denoted by this formula. And then I'm going to try to show the derivative of the two patterns of circle packing in Poincaré model. First, we hide all the line and then left out the point. Now we can see that in the figures, we show the derivative of the two patterns of circle packing in Poincaré model. That is a 6,4 case and 4,6 case. And then we can see that you take it as examples. This is the center of the circle in 6,4 case. And on the other hand, it is also the centers of hole in 4,6 case. And on the nearby point, it is just in opposite cases. We can show the result here. And also, we can also have, we discovered that it also have the same patterns in the spherical geometry. I hope you will appreciate our drawing. That's the end of our presentation. Thank you.